So the Banker's algorithm is based on each process declaring its maximum need of each resource. So each process, or we will have three matrices. One is the max that has the needs, the maximum needs of the processes. One is the allocation matrix that has the current allocations, and one is the need, which is the maximum minus the allocation. I think it will be better to look at the numerical example first. So we'll look into the numerical example. Okay, so we have this system with 5 processes, and 3 resources. So N is the number of processes, M is the number of resources. So in this case, in this example, N equals 5 and M equals 3 in this example. Okay, so what do we have here? For P0, we have, these are the maximum needs of P0. So the maximum needs are 7 of A, resource A, 5 of resource B, and 3 of resource C. And P0 currently has what is allocated to P0 at the moment: 0 instances of A, 1 instance of B, 0 instances of C. So this means that the projected need, or the future need, or the expected need for P0 is max minus allocation. The maximum minus what it currently has. So it's 7 minus 0, which is 7, 5 minus 1, which is 4, and 3 minus 0, which is 3. So these are the projected needs of process number 0. Okay. Process number 1, these are the maximum needs. This is what it currently has, and this is the need. So 3 minus 2 is 1, 2 minus 0 is 2, and 2 minus 0 is 2. So generally speaking, need equals max minus allocation. Now, we know the total number of instances of each resource: 10 of A, 5 of B, 7 of C. Given this number of instances, or these numbers of instances, and knowing what is currently being allocated, we can calculate what's available in the system. So what's available, what's currently available in the system, let's say resource A. The total is 10, and here is what is allocated. So what is currently allocated is 2 plus 3 plus 2. So that's 7. So 7 are currently allocated. Total is 10. So what we have available is 3. Resource B, total is 5. What is currently allocated is 1 plus 1, which is 2. 2 subtracted from 5 is 3. And resource C, we have total of 7. What is currently allocated is 5. So we have 2 available. So what is available now is 3, 3, 2. Okay. Now the concept of the safe sequence. Let's try to find the safe sequence. Now we scan the processes and we find a process whose needs can be satisfied using what is currently available, which is 332. Now, will 332 be good enough to satisfy the needs of P0? No, because it needs a lot more. Now, will it be good enough to satisfy the needs of P1? Yeah. So 332 are sufficient to satisfy the needs of P1. So P1 can be the first in the sequence. Okay? So P1 is, of course P1, is it the only the only process that can go first? No, it's not the only one, because P3 can go first as well, right? So we may have multiple safe sequences, but we would like to, whenever multiple processes are ready, we will pick the one that appears first in the original order. So we traverse this list in order. This is our convention. Any safe sequence is going to be correct. But our convention is to pick the process that appears first in this order, because in fact this is what the algorithm, the pseudocode that we will present later does. It will go through the processes in order, and it will pick the first process whose needs can be satisfied using what's available. Okay, so we'll put P1. Now, after P1 is done, how many instances of A will become available?
4.
Yeah, 4. Well, no, A.
I.
So P1, when P1 is done, it's going to release this. It's going to release what is allocated to it, not its needs. So its needs have not been used yet. Okay. But when P1 is available, it will release these. But see, these were not calculated, were not included in our calculation of what's available. So these are projected needs. So basically it will use these and release them, and then it will release what it currently has. So the net result after P1 completes is that we will have these back. Okay, the net result after P1 completes is having this vector back. So now, after P1 is completely done, we will get 2 more instances of A. So our availability is going to become 532. Okay. Any questions on this? Because this is the key step in the algorithm. Okay, now with 532, what do? We scan these processes and find a process whose needs can be satisfied using 532. Can we satisfy the needs of P0? No. P1 is done. We don't go back to a process that is already done. Can we satisfy the needs of P2? No. Can we satisfy the needs of P3? Yes. So the needs of P3 can be satisfied. And after P3 is done, so when P3 executes, it's going to get these and then release them. And then it's going to release these as well. So after P3 is done, we will add this to available. So we'll add 211 to available. That will give us 743. Okay. 743 came from adding 211. So did we put P3? So we said P3. So this is what will become available after P3 is done, 743. Okay, so this is 743, which is 532 plus this. Okay, now 743, we scan the processes. Now we can satisfy the needs of P0. So we put P0. Now after P0 is done, it's going to release one more instance of B. So we will have 753. Now with 753, can we satisfy we don't check the processes that we have already finished. So P1, P3, P0 are finished. So we need to check P2. Can we satisfy the needs of P2? Yes. So we put P2. Then we add what is allocated to P2 to available. So we add this to available. So 302, that's going to make it 10, 5, 5. Now, which process is left? P4. Can we satisfy its needs? definitely we can satisfy its needs. So P4 will release 2 more instances of resource C, so we'll have 2, 10, 5, and 7. 10, 5, and 7. Yeah, which is the total number of instances. So this is a safe sequence. Finding this safe sequence means that the system is currently in a safe state. Okay, yes?
So is there any possibility that we need much more than we have available? For example, if P4 needed 7 or let's say 1131 and we can't satisfy its needs, so there will be no safe sequence?
Well, we will assume that all of this analysis is based on the assumption that these maxima are right.
Okay.
So if a process requests more than the maximum, then all of our analysis will not make sense. Our analysis is done under the assumption that these are the maximum needs of the processes, that we know the maximum needs, and the maximum needs are correct. If they are incorrect, our analysis will be incorrect.
Thank you.
Okay? Okay, any questions? Yeah.
So there isn't one single correct state as long as all the resources are allocated in a way that all the processes get their resources. So there isn't a single correct safe sequence?
Yeah, so there may be multiple safe sequences. As I said here, we started with P1, but we could have started with P3 because the needs of P3 can be satisfied with 332. So we could have started with P3, and then we could have had other options as well. You know, at different points in the algorithm, you may have multiple options. But you take the first option, basically. That's a convention. That's our convention, or that's what the pseudocode that we will show does. Okay. Any other questions on this? Well, now we have shown that the system is in a safe state. Now, what if a process requests something? So what if process P1 requests 102, requests 1 instance of A, 0 instances of B, 2 instances of C? If P1 requests this, what will we do? We will temporarily satisfy the request, or we will pretend that we have satisfied the request by updating the allocation and the need of that process, and by updating the availability in the system, and then we redo the analysis. If we redo the analysis and it gives us a safe state, then we can grant the request and we commit. If we redo the analysis and it gives us an unsafe state, then we deny the request. So in this case, 102 means that for P1, so P1 will get 102. What's the original allocation of P1? The original allocation of P1, is 200. So we add to it 102. That gives us 302. Now the need, this is allocation 1. Need of 1, the current needs of process 1 are 122. Now what should we do with the need? Now we should subtract this from the need, because now it will no longer need these in the future. Now they have become now their current allocation. So we subtract 102 from 122, and that gives us 020. Okay? So we update the allocation and the need of P1. So the allocation becomes 302, the need becomes 020. What else do we need to update?
available?
Now,
Is it available resource?
available, yeah. So we have to subtract, we must subtract 102 from available. So our available changes from 332, available, changes from 332 to 332 minus 102, and that's 032, 230. So our available is now okay, yeah, 332 minus 102, it will become 230. Then we redo the analysis. Okay, when we redo the analysis, now this is 230. Now with 230, well, we can, with 230, which process can have its needs satisfied? Again, we'll find P1 again. And P1, then we'll add the allocation of P1, which is 302, and 302 will say 532. And in fact, in this particular example, this will put us where we were in the previous state. So everything else will be the same. So after this point, we'll get the same safe sequence, which is P3, P0, P2, P4. We will get the same safe sequence. Because after P1 releases what it has, we will get 532, and everything else will stay the same. Which means that this will put the system in a safe sequence, and we can go ahead with the request and satisfy or grant the request. Yeah.
So these are all the processes in need, but have they requested them yet or no? So like this stick table shows what each process needs, but hasn't asked for it yet?
No.
So
This is projected. This is what the need is, maximum minus allocation. So the process has declared its maximum need of each resource, and this is what it currently has. So if this is what it currently has, then its projected need, what it may request. So the need is may request, what the process may request in the future.
So then say there's only one safe sequence which involves P1 going first, and say P4 requests any resource, we'll just say no and have to wait until P1 asks for the resource.
Why? If
Well, say, like not specifically this example, but say there's a safe sequence where P1 has to go first. That's the only way it works, to be a safe sequence.
no, it's not unique.
But say it's a different example, where it is specifically.
So P3 can go first.
But say we have a different example where only P1 can go first.
Okay, so if there is an example and there is only one process.
There's only one like safe sequence.
Mhm.
So say P4 requests a resource, which would put it in an unsafe sequence. We'll just say no. I have to wait until P1 asks for the resource.
Well, we will not have to wait until a process requests. Well, things will get better when processes release some resources. So releasing resources what can make things better, not requesting resources. So we will have to wait if we deny a request, we're not giving that process that resource, and we are just waiting until some other process releases some resources.
Okay. So like, does a process need all its needs before it release all of them? Or can it release some before it gets the full needs? Like for example, could P1 finish just like that with 302 and just release those? Or does it need all zero? Does it need two more before it releases anything?
It will request them sometime in the future, but we don't know when.
So do we have to wait until that happens to give P4 anything? So for example, it's going to wait for P1 to get its needs.
Okay, so yes, so if we found this safe sequence, P1, P3, P0, P2, and this safe sequence is unique, are you asking that in this case we must execute the processes in this order? No, not necessarily, because This is like a worst case analysis.
Okay.
A worst case analysis of what may happen in the future. But what will actually happen in the future may be better than this.
Okay.
Okay. So it may be, that, one process like P2 terminates early and releases all of its resources, and then we will be in a better situation. Okay. So it's that's a good question, because avoidance means that we are trying to avoid deadlocks, and we are doing a worst case analysis based on the maximum needs. And we're saying that in the worst case, we will always find a sequence. We will find a way of executing processes in a certain order such that we don't have circular dependence. So we're saying that circular dependence is absolutely avoidable, even in the worst case.
Okay.
Yeah.
So when a process has allocated some of the available resources, is there a reason we wait till all those resources are released before we choose another process, as opposed to asking another process using what's currently available?
Okay, so let me clarify that this safe sequence, when we are constructing this safe sequence, we are not constructing a schedule. So this is not a schedule for executing processes. This is an analysis. This is a worst case analysis, not a schedule. So this is just a worst case analysis. Okay? Not a schedule. So we're not saying that P1 must go first, then P3. No. We are saying that in the worst case, there will be an ordering in which there is no circular dependence. So it's a worst case analysis, and the worst case analysis is saying, in the worst case, P1 can go because it doesn't have to wait for anyone. And if P1 can go, then eventually, P1 can go and doesn't have to wait for any of the others. So we're saying that eventually it will release what it has. We don't know when, but at some point it will release what it has, and we will have this. And then, when it has this, P3 can go. But this is not the only order in which things may end up happening in reality, right? So it's just like the worst case, a worst case analysis of the future. Okay? Okay. So now we have this safe sequence and we satisfied the request. Now, what if P4 requests 330? Can we satisfy it or not? The answer here is easy. We don't have 330. We have 230, so we cannot satisfy this request. Now, a more interesting question is, what if P0 requests 020? If P0 requests 020, let's now do the analysis on top of this. Now we have granted the P1's request. Let's do the analysis on top of this. If P0 requests 020, then the allocation of P2 of P0 allocation of P0 becomes 030, and the need of P0 becomes what will it become?
713?
723. 1. So you're subtracting this from this. So the need will become 723. Now what is available now? What will the available become? So you need to subtract 2 from 230, so it will become 210. with 210, now we scan the processes to see if we can satisfy the needs of any of them. So with 210. Okay. So can we satisfy the needs of P0? It's not 743, it's 723, but it's not going to make a difference. We cannot satisfy it with 210. Can we satisfy the needs of P1? No, because it needs 2 instances of B and we only have 1. So this is our available. Can we satisfy the needs of P2? Definitely not, because it needs 6 instances of A. Can we satisfy the needs of P3? No. So the answer is no. To satisfy the needs, we must be able to satisfy the needs for each resource. Don't look at the sum. Okay, so it's not about the sum. You must satisfy it for each and every resource. So which resource needs cannot be satisfied? C. It's requesting an instance of C, and we currently have 0 instances of C. So the answer is no. Here the answer is clearly no. So if we go ahead and satisfy or grant this request to P0, we will end up in an unsafe state. So to avoid deadlocks, we deny this request and we go back to this state. So we temporarily satisfied the request and did the analysis. That led to an unsafe state, so we undo the change and go back to the previous state, because the objective here is to maintain a safe state, to stay in a safe state. Okay? Questions?
So while this is going on, it's possible that new processes or new requests are coming in, right? So.
But no, we are assuming that we know what will come in the future, because we have the maximum need. So this analysis is done under the assumption that we know the maximum needs. So we know that the total number of instances of resource A that P0 will ever request is 7. So it will never request more than 7.
Right, but we can have, let's say, a P5 all of a sudden needs something, and would that...
Oh, a new process?
Yeah.
No, we are assuming here that we know the processes and we are doing the analysis for these processes and for the maximum needs of these processes. Now, if a new process comes in, then that process must declare its maximum needs, and we will have to do the analysis now with 6 processes instead of 5. Okay, so this is, by the way, this is this is not something that operating systems do. So we're not studying here an algorithm that operating systems do, because obviously it's unrealistic. That each process declares its maximum needs of each resource. So this is not a practical algorithm, in fact. Okay, and it's not an algorithm that real operating systems implement. Okay, now if we look at the pseudocode, this is the safety algorithm. So basically we have this work vector which we initialize to available, and then we update it. So work is here, is what we update. What we update here is work. So in fact, this should be called work, not available. What these numbers that we have been calculating here are work. And okay, so it's let's look at this. I think the pseudocode. The pseudocode will make more sense. So the pseudocode will first initialize each process to unfinished. So because our objective is to finish all processes, then it will try to finish all the processes. So it will be looping until done. When will we be done in this algorithm? We will be done if we finish all processes. In other words, if we find a safe sequence, or if we fail at some point to find a process whose needs can be satisfied. So if we either satisfy the needs of all processes, if we finish all of them, or if we fail at any point, if we can't find a process, if we go through all of them and we can't find any of them whose needs can be satisfied, then we have failed. So this is where we look for a process. So this is a loop that goes from process 0 to n minus 1. And it checks if this process is finished or not. If it's finished, then we don't have to check it again. You know, we don't want to find the same process over and over. So when we do P1 is finished, we check it as finished, and we never consider it again. We're done with it. And now we're comparing the needs of the process with work. This is what we were doing. So we were comparing the needs of a process like this with work. So we compare vector with vector. So this is a vector comparison, which means that we must compare every element in that vector. Each element in the vector with the corresponding element in the other vector. And this must be true for each element in both vectors. Then if this is true, we update work by adding work plus allocation. Work equals work plus allocation. Then we mark that process as finished, and we increment the finish count, and we break out of this loop that looks for a process. So here, you know, when we find P1, so we go through this loop, we find P1. After we find P1, we break out of the loop. So we have found one process. Then we will go through the loop again after the update. We update and we go through the loop again. Okay. And we finish if we find, if we finish all of them, or if we fail to find a process that is ready to go. Then we are, the algorithm is done. If the finish count is n, then it's safe, otherwise it's unsafe. Now, given that n is the number of processes and m is the number of resources, what's the running time of this algorithm? What's the running time of the algorithm given that we have n processes and m resources? M
times n.
So where is the m in the algorithm? Why is it m times n?
Because of the number of processes that we are doing. Or no?
Okay, so show me in the algorithm, where is the m? Okay, so how many times will this outer loop be executed? How many times will the outer loop that will find, how many?
N.
N, yeah. It's the number of products. So each time we'll try to find the product. So in the worst case, this will be n. And what about this? This loop, sorry. So for each n, to find the process, we scan the list of processes. So we have to find n processes, but to find, for each process, we will scan the list. So it's n squared. But, so this is n, worst case n, this is worst case n. But there is something hidden inside this loop. So it's not n squared, it's more than n squared. Because there is something hidden in this code. This code is not constant. This code here, not every operation here is takes constant time. Some operations here take more than constant time, a function of the input size.
The work equals work plus allocation, depending on the size of work and allocation.
Which is what?
Is that M?
Yeah.
Yeah, that's
M.
M.
M is the number of resources, N is the number of processes. So this operation here, this and this, this comparison compares two vectors, each is of size M, and this addition, it adds two vectors, and each one of them is of size M. So in fact, this operation is not a constant operation. It's there is a hidden loop in there. So there is a loop that goes from 1 to M, which is the number of resources, because you have to compare each and every element in each vector. So this is, need and work. And each one of them is a vector. So you'll have to compare. And this size is M. Okay, so this algorithm is N squared M. Okay, so this is an N squared M algorithm. Any questions on this? Now, this is the safety part. Now, the higher level algorithm is the algorithm that checks if for avoidance. So first of all, whenever a request comes in, it will first compare it with the need. It can be, because if it's not less than or equal to the need, so we reject it right away. First of all, we compare it with the needs of that process to check that the maxima that we have are correct. Because if a process requests something that exceeds its need, then the maxima that we were given were not right. So this means that this is an error, because the algorithm works under the assumption that we know the maximum needs. Then we compare that request with what's available. If it's less than or equal to what's available, we proceed, and then we pretend to allocate the requested resource by updating available, allocation, and need. And then we invoke this algorithm. Then we invoke this whole thing to check if the state is safe or not. If it's safe, then resources are allocated to PI. If it's unsafe, then PI must wait, and the original state is restored.